So this video we're going to explore vertical curves. To start out, let's contrast vertical curves and horizontal curves. So horizontal curves to start out. Horizontal curves, if you recall, are circular, and the diagram of a circular curve, or a horizontal curve, if I were to draw one here. So if this is a horizontal curve with an incoming tangent and an outgoing tangent. So that diagram is in plan view. We always diagram horizontal curves in plan view. What plan view means is if you are in an airplane looking straight down on the curve, or if you're taking aerial imagery from a drone looking straight down on a road, then the curves would appear in plan view. And they're circular. So vertical curves, on the other hand, are based on parabolas. They're parabolic curves, so I'll write that down. This means that the properties that we use for circles don't apply to vertical curves. Many reasons for this, mainly having to do with the lift that a vehicle gets as it comes into a vertical curve, as well as lines of sight, that sort of thing. So for whatever reason, we engineer vertical curves based on parabolas. When we consider the diagram of a vertical curve, it would be more like you're standing at a level, so here's you, and you're looking straight on at the curve, like you would see it like a hill. And we diagram vertical curves the same way. That's called profile view. So the diagram of a vertical curve is in profile view. And if we were to take the diagram of a vertical curve and look straight down on it, what would it look like? Just the diagram. It would look like a straight line, wouldn't it? So it wouldn't be very helpful except to maybe consider the stationing along a vertical curve. So if I move this up just a bit. Whereas horizontal curves, as we discussed, are subsets of circles, vertical curves are subsets of parabolas. So all of the properties of a parabola apply to vertical curves. And if you hear heavy panting, that's my dog. He's huge and he pants hard, so you probably picked that up. I noticed it in the video before. Sorry, can't do anything about it. I'm not going to lock him away. He may make an appearance at some point. So parabolas. Okay. And rather than, they can get, the diagrams of vertical curves can get pretty involved. So rather than torture you with my freehand styling, I diagrammed ahead of time vertical curve in Carlson, a couple of images. So let me bring those up. There you go. Magic of technology. There's a vertical curve. I'm going to make that a little bigger because I'm going to draw on it. In fact, let me make it as big as I can possibly get it. That will be helpful, so we don't lose any of it. So a vertical curve, like we said, is based on a parabola. And if we were to think about an incoming tangent to a vertical curve, it's a slope, right? It has a slope. So the incoming tangent we tend to say is a G1. I'm going to have to use darker colors here. G1, and the outgoing slope G2, so those are grades, and they're always given in percents. So we might say that G1 equals 3.0%. What that means, for every 100 feet in the x direction, we raise 2 feet in elevation. 3 feet in elevation. So that's a 3 foot every 100 feet of elevation change. So when we hit the curve, we call that the BVC, or the beginning of the vertical curve. And then if we were to carry that tangent out, the intersection with the outgoing tangent, or the extension thereof, is the PVI, or point of vertical intersection. And then finally the curve ends at the EVC, or end of vertical curvature. The book will change up that, that notation just a little bit once in a while, but for the most part they follow that notation. They use VPI instead of PVI. I will probably use PVI because I don't really, I'm used to PVI, so just know that they're the same. And if we were to consider the horizontal distance between the BVC and the EVC, we call that L. And that's a horizontal distance. So if we're standing looking at a vertical curve, then if we were to measure from the BVC all the way across to the EVC, the horizontal distance would be L. Okay? Now, I'm not going to prove it. In the book, section 25.5 has a proof of the fact that the horizontal distance from the BVC to the PVI is L over 2. And so the distance from the PVI, the horizontal distance from the PVI to the EVC has to be L over 2. Again, the proof is in the book. I'm not going to go through that proof because I'm going to take some time to derive some other things. So bottom line is the PVI occurs exactly halfway between the beginning and the end of the curve, horizontally, right? It does not mean that the same is true if we were to draw a straight line, because the EVC oftentimes can, well, most times, if not every time, occurs at a different elevation than the BVC. So remember, that's a horizontal distance that the L over 2 idea is true. Okay? So what is the, I'm going to change colors here real quick. What is the general equation of a parabola? If you remember, if we have some point P on that parabola, then y, the elevation of P, or the height of P, equals A, which is the elevation of the beginning of the curve, L of BVC, plus BX, where X is the distance along the curve, from the BVC to that point. So that's from the BVC to P, horizontal distance, and B is the slope of the incoming tangent. Okay? And let me just, as a side note, say that right here we're looking at a curve that is concave down, or going over a hill. The same laws are true for a curve that is concave up, or going through a valley. And then the last piece of that is plus some number cx squared. So that should look familiar to you. Y equals A plus BX plus CX squared. That's just the general formula for a parabola. So in engineering or surveying terms, we could say y of some point P on the curve, I'm down at the bottom here, equals y, the elevation at the beginning of the vertical curve, plus G1, or the incoming tangent, times the horizontal distance from the BVC to some point. So we could say the point is, I'm just going to put the point there on the curve. Let's say we're going right there. There's P. And if I draw a line there, then this here is X. And I have another diagram that will show this a little more clearly. So then to continue, so Y, the elevation of any point on the curve is equal to the elevation at the BVC plus the incoming grade times that distance, 2P, the horizontal distance P, plus some number Cx squared. So the only thing we haven't really defined yet is what this C is. Okay? And if you think about it, we have a known elevation YBVC, and we have this known grade, the incoming grade, and we want to know this elevation. What's missing in this? Well, there's no G2. Where is G2? We have to account for G2 because otherwise we have just a straight line, right? This is just the equation of a line until we add this component, the Cx squared. All right, so let's clean that up and look at a different diagram. There we go. Can make that a little bigger. That makes it easier to write. And we don't need that vertical. We know we're looking at vertical curves. So okay. So here we have our vertical curve, all the components we just talked about. And we're trying to figure out what this letter C is. So we have this logical conjecture that our vertical curve equation makes no use of our outgoing grade, or G2, the curve equation we just looked at. So our logical conjecture might be that C is somehow dependent on G2. So somehow dependent to some degree on G2. So G2 must be a component of that C2, and in fact it is. So let's confirm it. So C speaks to the rate of change, has to do with speaks to the rate of change in slope along the curve. And to visualize that, here we have our incoming tangent, and somehow that tangent has to change along the curve until we get to our outgoing tangent. So if you imagine a tangent line that's moving along the curve, and then it's there, and then it's there, C has built into it the rate of change of slope of the tangent line as it moves along the curve. All right. So let's look at what that C is. So we're going to approach this in two ways. The first way being the simpler. And what motivates this argument or this discussion is this distance right here. Okay. If we can use this distance, so I guess we would call this, so this would be the elevation of the EVC, and the vertical distance between the EVC and the projection of the EVC up to the line, which is the extension of G1. One of the ways that we can look at that is, first, let's look at what goes on here. this distance between some point on the curve and some point on the line G1, okay, or the extension of G1, either one. And this is motivated by, I'm going to zoom in here real quick and talk a little bit about first, if we were to consider this same, we'll call this H. If we were to consider an H over here, or an H just to the tangent line from the curve, there's a name for that. So the vertical distance from a point on the curve to the projection of that point on the tangent line, no matter which tangent line, G1 or G2, that's called the tangent offset. And that's going to be really important in some of the continuing work we do. I'm actually going to be looking a little bit more closely at tangent offset. Tangent offset is important in engineering because that's a method we use to base calculations in which we need to consider the clearance under a bridge or the clearance over a culvert. So that's what this tangent offset, it's a clearance, okay? So that's going to become really important. And we're going to use that idea here to some extent. So this H value, I'm going to clean this up, this H value that we're going to derive is a tangent offset. And we're just going to consider that tangent offset to the extension of G1. Okay, so real simply, do we have a way of getting the elevation of this point on the curve? We'll call it y of p. Let's call this point P. Then the elevation at point P is equal to just our parabola equation. So y of the BVC plus G1 x, x being the horizontal distance to P, plus this letter C that we're motivating here, x squared, right? So that is the elevation at point P. So if I can get the elevation of this, the projection up to the tangent line, then let's call it y prime of P, then H would equal y prime of P minus y of P, wouldn't it? Make sense? Elevation, the y prime elevation of P and then the elevation of P itself. The difference between those is our H. Okay. So let's do that. So we have our y of P, right? Now we just have to come up with our y prime of P. Well, this turns out to be really simple because what is this G1? This line of G1. It's just a straight line. And remember baby algebra where you use the slope of a line, y equals mx plus b, where m is the slope and b is the y-intercept. And this returns, given a point on the line, if you could plug in the x value, it spits back out the y value and you get coordinates. It's the same thing we're doing here. So y prime of P, that was an analogy to motivate the y prime of P. Y prime of P, come on, y prime of P equals the slope of our line times that horizontal distance, x, so the slope of our line is G1, right? Plus the y-intercept. Well, remember we start at the BVC, so the y-intercept is y BVC. Super simple. That part's easy. So then we have our y prime, that's this here. We have our y, which is this here, our y of p, of our point, that's that there. So if we just take the difference between those, we get our what we have, what we're looking for. So I'm just going to write this down. H H equals y prime of p minus y of p. If I substitute in those the terms that I came up with, I get then H equals y prime of p. So g1 of x plus y of the BVC minus the quantity yp. And we said yp is equal to this right here. Y BVC plus g1x plus cx squared. There we go. If we do the algebra, the astute students would notice that we're subtracting. If we move that minus into that set of terms, our g1 of x cancels out, our y BVC cancels out, and what we're left with is h equals minus cx squared. All right. So that's our h. That's our separation between the curve, a point on the curve, and that point's projection to the G1 line, or the extension of G1. So we can pick any point along here, and that's true, right? What if we were to pick EVC as our point? Then all we need is an x value, right? What is the x value at the EVC? Well, the x value, remember, is the distance from the BVC. Let me move this down just a little. Actually, isn't that just L? That's our L. So then we can substitute L in for x, and we get h equals minus CL squared. Oh, okay. So up here we have h equals minus CL squared. Okay, so that's part one. That's motivated by one method of calculating these. So we're going to continue, and we're going to motivate this distance here, this h value, differently. We'll call it h prime. I'm going to clean this up a little bit because it's pretty messy. Okay, I just cleaned this up a little bit. I'm going to zoom in because I'm about to draw a bunch of stuff on here, and it helps if this is as large as possible. So I'm going to make that as big as I can make it, have it make sense. All right, so I'm just going to highlight it. So we have this h equals minus CL squared. How can we use that? And remember, this whole thing is motivated by getting this distance here, this elevation here, from the EVC up to the extension of G1. And this is the extension of G1. Okay. So now, instead of looking at this tangent offset up from the curve up to the extension of G1, instead of looking at that, let's consider just the separation between the tangents. Let's just see what happens, okay? And let's call that h prime. Okay, so that's what we're going to look at. Erase all that. And so, firstly, let's consider a point on our tangent line. can we get that? Well, sure. We've already said we can get, let's call that y prime of some horizontal distance x along our tangent line equals our slope g1x plus y BVC. Okay, so that gives us the elevation of this point. Let's call it P prime. So that we have. So let me just write this off to the side here where we can keep track of it. So y prime equals g1x plus y BVC. Simple enough. So then let's say we go down a perfectly vertical distance and we're interested in the elevation here. And we'll call that y. How do we get that? It's pretty much the same thing. The reason we want to get that is because here h equals y prime minus y, right? So if we can figure out the elevation of y at, we'll call it P, then we can perform that subtraction. All right. So let's start with the elevation of the PVI. Okay. Let's see, what's the elevation of the PVI? Well, we use our G, it's going to be y PVI equals G1 of x, let's call it x PVI, plus y BVC. Okay, so the elevation of the PVI is equal to G1, our grade, incoming grade, times the horizontal distance here, plus y BVC, the elevation here. But what did we say before this was equal to? What is the x value at the PVI? That's L over 2, right? Okay. So we can say that y PVI, I can get rid of the x there, and say y PVI equals G1 L over 2 plus y BVC. And let's keep track of that. And I'm going to keep track of it over to the left side here. Y PVI equals G1 L over 2 plus y BVC. Okay, well that's pretty easy. It's a point on a line. We just use the point slope formula, good old point slope formula. So how do we get down to our YP here? How do we get down here from the PVI to here? Well, if we consider this the point PVI as our starting point, well then the elevation of YP here would be the elevation of the PVI plus, let's say here, YP equals YPVI, the elevation of our PVI, plus this distance, let's call it something different. Let's call that D, just so we're not getting the x's confused, plus D, or sorry, G2D, right? Isn't that true? I mean, the y of our point then is equal to y PVI plus G2D. That's just the slope of another line. Well, we have an equation for the PVI up here. So now we can say, if we substitute that in, just go put that into there. I don't want to get too convoluted here. I just wanted to demonstrate. Then we have y of p equals ypvi, which we said was equal to this. So I'm going to put that in. G1x, or sorry, we gave x a new name. G1 L over 2 plus y BVC plus YPV, or plus G2 D. So, don't get too confused. This together right here is the YPVI. So, YPVI plus G2D. That's all I did. I just rewrote this. Okay. So now we have our y of p. This is the elevation of our point. Elevation of our point. And everything is known here except for this d value, right? So if this is our yp, that should be a yp there, then our h prime here, remember our goal is to get the distance here, which we said is our y prime minus our yp, right? And we just solve for yp here, and we solve for y prime and put it up here. So I'm just going to put my yp here. So y sub p equals g1 L over 2 plus y BVC plus G2D. Okay. So now we have, I'm running out of space here. So if we said that h prime is equal to y prime minus yp. Okay, that gives us our h prime there. So let's write that out. Let me see if I can make a space there in that central red. Okay, well I can't erase that red line, but I drew some gray over it. I'm going to write in purple now. So we have h prime equals y prime minus yp, which equals, what's our y prime? Our y prime is g1 of x plus y BVC. And remember here x is all the way from the BVC as far out as we want to take that y prime x value, right? And then that is minus the quantity of yp, which is g1 L over 2 plus y BVC plus G2D, where D is just this distance from the YPVI. Okay, well, not bad. I'm going to take this equation and put it on black space so that it's easier to work with. We don't need the diagram anymore. We're just going to simplify that. Before I do, I want to just extend this idea. So now we need to do something with this x value. We need to do something with this d value, right? Everything else is known. We have the elevation of our BVC. We have our incoming tangent. We have our outgoing tangent. We have L, right? We have L. The only thing we don't know now is x and d. So let's try a mind experience, or experiment, a thought experiment. What if we let this point continue moving until we get all the way to the end of the vertical curve? So we consider what this h prime is at this location at the EVC. Well, d, let's see, x, let's start with x. X would be this entire length here. So at that point, x equals L. And what about the d? That goes all the way to there, but whoop, went too far. There. From the PVI, what is that? Well, d equals L over 2. So now we can substitute those into there. And I'm going to scroll this up so that I can have space to work. So let me change colors here because purple won't work well on that. All right, so what we were left with was h prime equals g1x plus y BVC minus g1 L over 2 plus y BVC plus g2d. Okay, and we said x equals L, and we found a place where x equals L and d equals L over 2. Okay, so if we clean that up, we get g1 L over 2 plus y BVC minus, I'm going to distribute that minus in, so minus g1 L over 2 minus y BVC, I'm just distributing the minus, minus g2 L over 2. So I substituted these values, distributed in the negative, and this is what I ended up with. Now, we can look at some of these values. So I have g1 L over 2 minus g1 L over 2, y BVC minus y BVC. So I have oops, I see my mistake. And you probably saw it too. So this isn't g1 L over 2, it's g1 L, right? So what I did, x is equal to L, not L over 2. So there we go. So g1 L plus y BVC. So these don't quite cancel out. I knew I made a mistake. So g1 L over 2. There we go. So we can clean this up. Still, the y BVCs go away, right? And we have, what is g1L minus g1L over 2? No, that's g1L over 2. g1L minus g1 times half of L, well, that's just a g1L over 2. If you don't believe me, g1L minus g1L over 2, take out the g1, and that's g1L minus L over 2. Well, that's g1 L over 2, right? Okay, so still just simplifying this set of terms. The YBVCs go away. We've dealt with that. We've dealt with that. All we're left with is this. So G1L over 2 minus G2L over 2. All of that to get something that simple. Okay. And all of that is equal to H prime. But here's the magic. Let me pull this down. Remember what H prime is. Oh, I pulled it down too far. Remember H prime, we were considering now as being over here at the EVC. So H prime is this distance here. That's what we were going for. Well, that's the same as H, right? So that gives us H prime equals H, and H equals this minus CL squared. Aha! So now we can pull in that C and solve for it. So I'm going to go back to the equations. So H equals minus CL squared with H prime equaling H. So now can't I just set these equal to each other to say minus CL squared equals G1 L over 2 minus G2 L over 2, right? And if I solve for C, I have that little minus there. I'm not going to go through all the steps of solving, it's just simple algebra. I end up with C equals G2 minus G1 over 2L. Okay, so C, G2 is a constant of our curve, G1 is a constant of our curve, and L is a constant of our curve. That's the total length of the curve. We have a constant. So it doesn't matter that we were building it from different parts along the curve. We said, okay, let's consider what the truth is at the end of the curve, and it gave us constants. So that means C remains constant. So now we know our C. And our equation becomes, I'm going to leave that there. So our equation for the parabola, y of some point P, the elevation of some point P equals y of the beginning of our curve plus G1. Oh, and by the way, we were right. Here's that G2 that we knew had to be somewhere in C, right? So G1 x, where x is the horizontal distance to some point P, so I'll put x sub P, plus, and we said cx squared, so we just put that in, G2 minus G1 over 2L x squared. So now, to get the elevation of any point, we have all of our known parameters. YBVC, G1, G2, L are all known. So at any horizontal distance, we can get an elevation. Now, just before I wrap up, I want to talk about the rate of change real quick. So the book likes to use, instead of G2 minus G1, this here, they like to use R over 2 x squared. The reason is that the rate of change of a grade, so the rate of change of a grade along a curve at some, or I could say any, given point is R equals the difference in the slopes, so G2 minus G1, over L. So the difference in slope divided along the length of the curve. Well, that looks really similar to our C up here. So that just means if you do that math and figure out, you get C equals R over 2. If you take this, you take out the half. I can demonstrate that for you, but it's really simple algebra. So if you take this, divide it by 2, take R divided by 2, 1/2 R equals 1/2. I guess I am going to do this for you. G2 minus G1, just multiply both sides by 1/2 over L, and that equals G2 minus G1 over 2L equals C. So I could have started there. That's where that comes from. So that I just thought it was important to go through those steps so you can see where that coefficient of the x squared comes from, how it incorporates the the outgoing grade, the incoming grade, and with that you can get any elevation along a curve. The other value is that in proving this, we were motivated by the concept of tangent offset. Remember I said how important that was, tangent offset? Well, it turns out the tangent offset values, so if I have some curve and I have tangents, really dumb, but this is the tangent offset. So that tangent offset, and it makes sense if you think about it, that tangent offset is this. So Cx squared equals tangent offset at any given point. And it makes sense, right? If we're going along a line, then we have to consider some difference. This part here is just a line. So we have to add something, even if that's a negative number that we add, to get back to the curve. Well, that difference that we add is the tangent offset. Okay, so that's going to be important for the next little segment of vertical curves we do. Cx squared is the tangent offset. I think that's it. So anyway, this should set you up to at least get started on the vertical curve portion of the problem. I posted some examples on Canvas that you can use to help with the homework problem for vertical curves. So go ahead and give that a try. Email with questions, and I'm happy to entertain that. All right? Thanks.